The next topic in Chapter 4 we're going to look at is acids and bases. Here are some examples of acids and bases you probably have at home. Starting on the left, we have some Drano. Drano is a strong base. Then we have some vitamin C. Vitamin C is a weak acid. We have muriatic acid. This is a strong acid that you can buy in like a Home Depot or a Lowe's. This is really sulfuric acid. And then we have vinegar. This is a weak acid. It's really acetic acid. And then we have some original index that contains ammonia. And ammonia is a weak base. Properties of acids. Acids have a sour taste. Vinegar owes its taste to acetic acid. Citrus fruits contain citric acid. So acids are all around us. In fact, one of our taste buds is for acids. And we actually like the taste of acids. But we also want to combine that taste with something sweet. So a lot of times when foods are acidic, companies will add sugar to them to try to offset the sour taste that you might get from it. So there are things that contain a lot of sugar that you might not be aware of. For instance, tomato sauce contains a lot of sugar because tomatoes are pretty acidic. Acids change the color of dyes from plants. In fact, this is one of the properties that we have for acids. There are many different plant dyes that are affected by acids. The most common one is called litmus. Litmus is red in an acid. Acids also react with certain metals to produce hydrogen gas. Here's an example here with magnesium metal, which is a pretty reactive metal. Now, not all metals react with acids. In fact, gold doesn't, and copper, for the most part, doesn't, and even silver is not that chemically active with acids. But all the alkali metals, obviously, and the alkali earth metals would all react pretty vigorously with acids. And even our common metals like iron and lead would react with acids as well. And you notice that we're getting the hydrogen gas produced, and you can see it right over there, in the picture. Acids react with the carbonates and bicarbonates to produce carbon dioxide gas. And here's that equation there. Now the carbon dioxide, as we see with my arrow go here we are, here's the carbon dioxide gas, and that's actually coming from the carbonate. So calcium carbonate is an example of a very common carbonate you can buy in a store, and you probably buy it as Tums or Rolaids. And all acid solutions conduct electricity. Weak acids conduct electricity weakly. Strong acids conduct it very strongly because they produce a lot of ions. Now bases, on the other hand, have a bitter taste, not a sour taste like acids. And some vegetables are bitter, especially green vegetables. Bases feel slippery, and you feel the slipperiness in your hands, whether you're talking about soaps or detergents, or even something, let's see, that you might have at home. Even mouthwash would feel a little bit slippery, because that has a base in it as well. And we also have, again, plant dyes being affected by bases. And I mentioned litmus before. Litmus was red in an acid and it's blue in a base. And solutions of bases also produce a lot of ions, so they conduct electricity as well. We can have strong bases and we can have weak bases. An example here would be ammonia. That's a weak base, and hydroxide is a strong base. Now there are a couple of different theories that we have about acids and bases, so we're going to go over them one at a time, and they're named from the people that came up with them. So the first one is by Svante Arrhenius. So we call it Arrhenius acid. So a substance that reacts with water and produces hydrogen ions in the water. Now hydrogen ions, H positive, are not thought to exist by themselves. They actually combine. Here's the hydrogen here from the HCl. This hydrogen really comes over and bonds right here to the water, and that produces our H3O, which is called hydronium. So in water we really have hydronium ions, not hydrogen ions. We still kind of think of it that way. For Arrhenius acids you have to have water involved. No other liquid will do. And Arrhenius bases produce hydroxide ions in water. And if we take a look down here, notice first of all we have a double arrow versus the single arrow up top. the double arrow tells us that this is a weak base, and so we have ammonia reacting with water. Now in this case, a hydrogen from the water comes and bonds to the nitrogen here of the ammonia, and we wind up getting ammonium and hydroxide ions. So no matter what, an Arrhenius base produces hydroxide ions in water. Acid produces hydronium ions in water. Now the other type of definition that we're going to see is called a Bronsted acid base. This is from a Danish fellow, Bronsted. And so in this case we have proton donors and proton acceptors. Everything that was an Arrhenius acid is still going to be a Bronsted acid. Everything that's an Arrhenius base will be a Bronsted base. The difference is that many other things can be Bronsted bases that wouldn't be an Arrhenius base. Now here's an example that we had a moment ago. This is ammonia again, and ammonia is reacting with water, and it is producing hydroxide ions, so it's an Arrhenius base. Now let's see about a Bronsted base. Well, here the water is acting like an acid because it's donating a proton, which is an H positive, and the ammonia is acting like a base because it's accepting the H positive. But we also have a reversible reaction here. You notice the double arrows indicate it's weakly reacting, but it also reacts in the reverse direction. So in the reverse direction, the ammonium ion is the acid, and the hydroxide is a base. So here, in a Bronsted acid-base system, we have two acids and two bases. So in order for a substance to be a Bronsted acid, it has to contain one ionizable proton, and proton really meaning a hydrogen atom. Now we can classify acids different ways, and one way to classify them is by the number of protons they can donate. So monoprotic acids can only donate one proton when they act as acids. Now here are three examples. HCl, which is hydrochloric acid, HNO3, which is nitric acid, and CH3COOH, which is acetic acid. Don't worry about the formulas. You don't have to memorize these acids at all. You notice that the acetic acid is weak. We can tell by the double arrow. Okay, but they're only donating one proton. So we have monoprotic, then we could have diprotic. In the diprotic example, we have a sulfuric acid. And you notice that for sulfuric acid, we have one step that goes very well to the right, where it donates one proton, and then it becomes this ion here, which is called bisulfate. And then this bisulfate ion can also donate that second hydrogen ion. So it isn't like the H2SO4 donates two protons all at once. It's one at a time. And this step also tells you that it doesn't donate the second one 100%. So after diprotic, we could have triprotic. An example here is phosphoric acid. And you notice, just like we had with the sulfuric, here's my arrow, just as we have with sulfuric, the H3PO4 can donate a proton one step at a time. Then once we get down to phosphate at the end, that's the end of it, because this has no more protons to donate. One thing you cannot tell from this is which of these steps goes the best. It's always the first step. So in the first step, we get the most hydrogen ions. The double arrow is telling us even the most is not a lot. But then the second and third steps give us even fewer. So monoprotic, diprotic, triprotic, it's just a way of classifying some acids. Table 4.3 in the book gives you this small grouping of them. And it might give you the wrong impression. It looks like there are more strong acids than weak acids, but that's really the opposite. They're just not showing you all the different weak acids that there are. Right. Neutralization reactions. Acids and bases can neutralize each other. And when they do, they produce, well, in this case, we're going to see different products. The first set we're going to see are salts and water. So our example is going to be hydrochloric acid and sodium hydroxide. And you notice that the salt we're getting is sodium chloride. So the salt, part of the salt comes from the acid and part comes from the base. And you can see here that the metal comes from the base and the nonmetal, the chloride, is coming from the acid. Now if we write an ionic equation for this, we'll get all these ions here, and then if we eliminate the spectator ions, the chloride and the sodium, we wind up with the net ionic equation for this reaction. So now we can see why acids and bases can neutralize each other, because they wind up making water. And once you make water, the water pretty much stays together. So this is one example. Now we're going to take a look at a couple more right after you answer this question. Alright, now let's see if you can write equations for these three reactions between acids and bases. And what you really have to do is come up with the formula for the salt, because all of them are going to make water as a product. And we can tell that because anytime we have hydroxide and we have an acid, we're going to get water. And the other thing is, what's the salt? So we saw earlier that hydrochloric acid and sodium hydroxide gave us sodium chloride. So for this first one, we're going to get water and potassium chloride. Now I'm writing water HOH just because it's easier for me typing it, but also that's the way many times we write it when we talk about acids and bases. Now let's see if you can come up with the next two. So I might want to pause at this point and copy down the next two and try to come up with, it's really the formula of the salt. And so remember, when you come up with the salt formula, there's my arrow again, the salt formula will depend on the metal and the anion from the acid. And remember the charges now, so the charges have to add up to 0. Alright, so give it a shot, and we'll come back and we can see the answers. Okay, so for this one, you would get water and sodium sulfate. Now if you notice, the equation isn't balanced. So to balance it off, we'd have to get 2 sodiums on the left. And that's going to make 2 water on the right. So that's our final answer there. So why Na2SO4? And that's because sodium has only a charge of +1, but sulfate has a charge of -2. And then we have the last one here, nitric acid and calcium hydroxide. We're going to get water and calcium nitrate. And again, we'll have to balance off the equation. And here we go here. So you should be able then to figure out the formula for the salt when you add an acid to a hydroxide. Okay. Next reaction. Now we're going to take a look at using a weak acid and a base. With a weak acid, it's a little bit different. Now the example that we're going to use is HCN, which is hydrocyanic acid, and sodium hydroxide. If I write the ionic equation, I would get this. Now you notice the HCN, because it's a weak acid, really doesn't ionize very well. So we're keeping it together as HCN. Now what ions can I eliminate? Well, I can eliminate the sodium. And that looks about it. So my net ionic equation then looks like this. It's a little bit different than the one we had in the previous slide. But you notice again, we're making water. We're making cyanide. Okay. Now this is the last equation that we're going to take a look at, producing a gas. And the gas we're going to see is CO2. So we have a hydroxide, I'm sorry, not hydroxide, but a carbonate and an acid or a bicarbonate. We're going to get 3 products. So here in my example, I have HCl, which is hydrochloric acid, and then we have sodium carbonate, and I get 3 products. This is my ionic equation, and what ions can I eliminate? I definitely get rid of the sodium. I can get rid of the chloride, and that looks like about it. If I bring down what's left, I have this. So you notice again we're making water. In fact, in each case we made water as a product. So we're not seeing the salt in our net ionic equation because the sodium chloride stays dissolved, and we eliminated it from the ionic equation. So carbonates and bicarbonates give you CO2 as a product.